Hi folks, welcome back to Physics with Captain Rod, making this one to help you out with number 24 in your homework here. So you folks have seen quite a few problems like this. We have this system here that starts in this configuration. And it says that the system starts to move or accelerate. Now, some things to start paying notice of in these problems, right? You'll notice that right here, A is not on any wheels of any kind, right? In physics problems, typically when people mean that something's going to be a low friction scenario, usually they put those on little wheels or something like that. Not always, but usually. So this is not on wheels. Now I know it might look like it's levitating there a little tiny bit, but that's not the intention here. The intention is A is sliding across this surface. So at first glance right here, one of the first things we have to ask ourselves is, okay, frictional force, yes or no? And as you read the problem, if you actually read part A, it says find the frictional force acting on A. So there should give you your answer on whether or not there's a frictional force acting on A. Now, it also says to use principles of work and energy. So here's position 1. Draw the system at position 2. Right? B will have moved down to here. A will have moved over to here. Okay. Write out the work-energy theorem as usual. Okay. Now let's chat about this. I would probably, put a datum at the ground. Now that means that mass B has a potential energy, so you're going to have to take that into account. Now mass A and the pulley have potential energies as well, but they're not changing. So if they're not changing, you can toss them. Okay, so that's this term now talked about. System is released from rest. That tells you something about this term. Potential energy 2. When we start thinking about this. Now remember, mass A and the pulley we tossed. Mass B is now down here. That should tell you what to do with the PE2 term. Right? Now let's talk about KE2. Right? Mass A. Is it moving? Yes or no? If the answer is yes, you have to put a 1/2 mv squared for it. A 1/2 mass A times v squared. Okay, mass B, this thing, is it moving? And the answer is yes again. So you need another kinetic energy term for mass B, a 1/2 m mass B times v squared. Also though, the pulley has a significant mass in this problem. Right? In a lot of the problems I gave you, the pulley was hollow or did not have a significant mass, but in this one it does. It does have a significant mass, and its moment of inertia is given right here. So you have a 1/2 I omega squared for the pulley that goes into that equation, under the KE2. So your KE2 should have 3 terms. Okay, next. Let's talk about the work term. This one's not quite so subtle. All right. Draw free bodies of this object and this one. Right? Now, hopefully you've seen enough of these to realize we don't need to worry about the mg for mass B because we're taking that into account. Hopefully you've seen enough of these that you know now we also, right, as long as we define our system like this, all of it together, you don't have to worry about the tension either. It becomes, I guess, technically it's not an internal force, but the net work done by the tensions is 0 in this. The work term is reserved typically for forces that are adding energy or taking energy away from the system, and the tension isn't doing that. But when you look at this free body right here, The friction is an external force that is robbing the system of energy. Because if you think about what will happen, as this object slides across this surface, the surface will get warm ever so slightly, right? And that's a manifestation of some of the kinetic energy is being robbed from the system. Okay? So you are going to have a work term here. And then you got to decide, is it positive or negative, right? Well, let me help you out with that. The frictional force on this object, which way is it, right? Look at your free body and decide that. And then, which way is this object moving? Is it right or left? All right, and remember the sign convention. When the force and the velocity are in the same direction, the work is positive. When the force and the velocity are in opposite directions, the work is negative. Right? So that should allow you to get an equation written out. It's going to be, reasonably long and have a lot of stuff here. And that equation should have an unknown F in it. Over on the right, it should have a pair of velocities, but those velocities are the same. Because if A moves 1 foot, B also moves 1 foot. And it's also going to have an angular velocity. So in effect, the right-hand side kind of looks like it has two unknowns. Okay, but those unknowns are linked. They're linked at the pulley. As this spot kind of moves around, there's a distance S, which is equal to R times change in theta. And if you divide by time, the S, right, which is a distance, becomes a V. It becomes a speed. And the change in theta over change in time is what we call the angular velocity. All right, so that's going to allow you to, I would solve for this and sub it into that KE2 term, and that'll get rid of the angular speed. And that should come pretty close to doing it. Let's see, what else are you going to need? Oh, how do we get the V2s? Well, the object moves 1.5 meters in 6 seconds. Now, most everybody I've ever seen will take the 1.5 meters, divide by 6 seconds, and get a number with units of meter per second. And it's not wrong to do so, but you have to realize what you just calculated. You just calculated the average velocity over the time interval over which this thing's moving. In the work energy theorem, these are instantaneous velocities. Those are the final velocities. Just keep that in mind when you work this problem out. So that should get you through it, I hope. Have a great day.